cream usually. So is okay. Right. So I would thank the organizer for the invitation, but there was no invitation. So yeah. But I'm very happy to be here. So at Caltech, we're spending this year at Google. So sharing between the two. I want to talk about. So what I want to do is kind of in the reverse direction of the other talks today, maybe yesterday. So this workshop, we are seeing a lot of applications of convex optimization to quantum information and to quantum computing, right? Using as a tool to understand better quantum information, quantum computing. What I want to do here is, maybe it's the opposite, is I want to see whether quantum computation, one day when we have a quantum computer, if we can use it to solve convex optimizations better or faster, in particular. And I'll show you in some cases, yes, but there's a lot still that we have to figure out. So it's work done with a lot of collaborators, and I mentioned their names when I mentioned the specific result. So if you, let me just start it. If you have any question, just stop me during the talk. All right, so we would like to build a quantum computer one day because we have all these quantum algorithms that we could run on it. So maybe we can split into 3 groups. One is these problems for which we have these huge speedups, these exponential speedups. One example is to simulate quantum physics, where you just have, for example, I don't know, you wanna understand high T superconductivity, right? So that's very hard classically. Maybe for quantum computer you can do it better. Then, okay, that's what was the original problem that Feynman already pointed out right in the beginning of quantum computing. Then what really got many people excited was Shor finding this quantum algorithm for factoring, which is very important in cryptography, where there is exponential speed up there too. So completely outside of physics, we have these problems for which if you have a quantum computer, we can have these very meaningful speed ups. Then more recently, there's this work to solve linear equations faster as well. There are some conditions, we'll get to that later. Then for some other problems, we cannot really get exponential speedups, but you can still get some speedups, and that's still interesting. So for example, Grover's algorithm, we can just find a marked element in a list of n elements in time square root of n, if you can query the list in superposition. Classically, you need linear time in n. And that's the best we can do. Quantum as well is square root n. So there is no exponential speedup, but there is still some quadratic speedups. And there is a bunch of proposals that we can call heuristics. These are algorithms that we can run on a quantum computer, but we cannot analyze them, how well they work. And because we don't have the quantum computer yet, we don't really know, right? But maybe one day, as heuristics are so important in classical computation, they will show up important too. So there is quantum annealing, if you want to approximate some hard optimization problem. There's a more digital version of it, which is this quantum approximate optimization algorithm. There's a bunch of proposals in quantum machine learning and so on. And then, maybe you can play a game, say what is the time scale, right, to have these things. Maybe exponential speedups, we need a universal quantum computer with error correction, million of qubits. This will take a long time, right? Maybe 25 years. Polynomial speedups, well, we have to have a quantum computer, universal, and it has to be cheap enough, right, that this quadratic speedup already pays off. So maybe 35 years. How about heuristics? And that's interesting, right? Because it could be that actually very soon we might be able to get some gains from them. It might be never, because we don't know yet, right? But let's focus on this, why 5 years? And I think that's an interesting development that I want to build on in the talk. And this is, so first the challenge is just to find algorithms right in each one of these classes, just to understand better what we can do with a quantum computer. So we have soon these early quantum computers. So this has been termed a NISQ era, meaning noisy intermediate scale quantum. So what is happening right now? Well, of course, we're still a long way from having a quantum computer universal that can, for example, factor a big number, 300-digit number, for example. But these early quantum computers with like 50 to 100 qubits, no error correction, but with low enough error rates, maybe like 0.5% for a 2-qubit gates, they are around the corner, right? So there's like Google, IBM, experiments in Harvard and other places. They're on the verge of having them, right? And then this is interesting, it's something we didn't have before, right? And the question is, can we do anything interesting with them, right? With these early quantum computers. Which is a very non-trivial question, right? Because, well, they have, if you just simulate them naively on a classic computer, you cannot. Right? 100 qubits is too much for that, right? But they are noisy, so it's not clear if you can run anything interesting. So one benchmark and is what people call this supremacy, quantum supremacy. So the idea is that, as I mentioned, we'll probably cross this regime where quantum devices offer computational speedups over classic computing with around 50 qubits. And this is what we call quantum supremacy. What I mean by that is just you can run something on the quantum computer that's, if you would try to do the same thing classically, it would take much, much longer. But you don't care what you run. Okay, you just create an artificial task that is very easy for the quantum computer, but which is hard for the classic computer. And what is this task? Well, it's just to simulate some quantum evolution, some quantum circuit, right? And the most promising one is just you run a random quantum circuit there. You just measure all the qubits in the computational basis in the end. And your task is to sample from this probability distribution. So quantumly you can do, right, by definition. Classically, there is reasons to believe that that's hard. And with already like 50 qubits, it becomes intractable. Even the best supercomputer will take a long time. In quantum, with the noise levels that we have at the moment, or that we expect to have in these early quantum computers, it seems we could do some version of this. So it's really nice, right? It's like a benchmark. We are already in this new territory where there might be interesting algorithmic applications, but it's a benchmark, right? It's not really, no one wants to solve this problem, right, per se. So we can say they don't solve yet a useful problem. And then, of course, there is heuristics that people will try once we have these computers, like quantum annealing. But quantum annealing is tricky because there is quantum Monte Carlo, and there's a lot of work which shows that actually quantum Monte Carlo, for all the examples we know, performs just as well as quantum annealing. So that's like a drawback. There is quantum chemistry that maybe you can do some with variation eigensolvers. But first, we don't know if this is just an ansatz, right? We don't know if this ansatz is good. Second, there is some problem with like sampling complexity, which gets very high, even for some simple molecules like nitrobenzene. So there are things to try, but it's not clear if they will go anywhere, right? So the message here is just we should look for new things, right? We should look for other things as well. And that will be one of the points of what I want to show you here. Okay, so the message of the talk will be that one of the things we should try is to solve a particular convex optimization problem, right? That's why it fits here in this workshop. So what is this problem? Is what we call semidefinite programming. Okay, everyone mentioned this morning already, so I don't. This is not new to anyone here, but let's just go over the notation. So it's a class of optimization, convex optimization problems. What do we want to do? We want to maximize a linear function over some linear constraints over the set of positive semidefinite matrices. So the input of the problem are n by n S-sparse matrices C and A1 up to AM, and real numbers B1 up to Bm. And then we want to maximize over X, which is an n by n positive semidefinite matrix, trace Cx, this linear function. And the constraint is that trace AJX has to be smaller than BJ. Okay, so that's a general SCP, you can write like that. And small m will be the number of constraints. So there are three numbers, n, the dimension, s, the sparsity, and m, the number of constraints. So the sparsity just means that in each row of the matrices, there is at most s non-zero elements. There is another number that I also need to state the results, which is an upper bound R on the trace of the optimal solution. Okay, so that's a positive semidefinite matrix, so the trace is like the one norm, right? So this is just R is an upper bound on the size of the optimal solution. And our algorithms, they will depend on this R as well. So and it has some implications, but we'll see that later. What is the output? Well, it's just X, right? We want to output some optimal solution, or maybe you're just happy if you output some approximation of the optimal value, right? So a particular case is linear programming, of course, if all the matrices are diagonal, right? And that's also important. There are many applications, right? So these are just copied from Wikipedia, so I cannot really explain what they are. But one that I can explain, of course, right? Which is the point of this workshop, the quantum information theory, this is used all the time, SDPs, right? Yes, Laura. It's a good question, yeah. So classically, indeed, right, it's in a piece of paper. Quantumly, you have to debate, right? And this will be important, yeah. I'll get to that, yeah. Thank you. Or also for approximating NP hard problems, right? So it turns out that there is all this NP hard problems that we like to solve. We cannot solve them exactly, but we can approximate them. And actually, there's a lot of interesting results which show that the best algorithms to approximate them are SDPs. Okay, so there's a threshold you can approximate up to that level with SDPs. Beyond that is NP hard, or like unique games hard. So they are very successful in approximating hard combinatorial optimization problems. And we'll get to that later too. Okay, great. So they are very general, but why they're important? Also because there are good algorithms classically as well, right? So classically, there are two classes of algorithms. One are interior point methods, and they run in this time, the state of the art at the moment. It's like m squared ns plus mn squared times log r over epsilon. Epsilon is the accuracy. This would just be, we want to compute some x, which achieves the optimal up to plus minus epsilon, some additive error epsilon. So this is good if you are lenient with r and epsilon, but you want the best performance possible in terms of m, n, and s. Then this multiplicative weight method improves on that. It gives like time m times n times s, but bad dependence on r over epsilon, right? So, but maybe sometimes you want to use it, right? So these are the two. There's a question? I can give you later, yeah. So, and I must say this is the theoretical bound, right? Of course, maybe empirically you can do better, but actually empiric is pretty close to this. But this is Sid Ford and someone else. One of the authors is Sid Ford, but I'll give you the reference. Okay, so the question is, can quantum help, right? And let me make the two cases. First, maybe yes. One reason is LP, which is a particular case of SDPs, is a generalization of linear equations, right? You change from equalities to inequalities. And there are exponential speedups for linear equations, right? At least if you formulate in the right way. Also, SDPs, they are very natural in quantum mechanics, right? So they can be reduced efficiently to the following particular SDPs. So you're just given a bunch of Hermitian matrices, A1 to AM, and some real numbers, B1 to BM. And your task is to find whether there exists a density matrix rho such that the expectation value of rho on AI is smaller than BI, right? So it's like it has a very basic formulation. This looks more general, and it is, but you can reduce to this one like efficiently. So if you want, you can just think of SDPs as this quantum problem. On the other hand, maybe it doesn't, right? So we can show a quantum lower bound of this form, square root of n plus square root of m, in like the standard oracle. I'll tell you what it is later, but it's the oracle that like usually assume for this kind of problems. So there will not be like exponential speedups, at least in this standard oracle. So that will be an issue that we'll analyze later. And even these polynomial speedups, we didn't know how to do before, right? So, so the point of this talk is to show that you can get a speedup with quantum computing, and the point will be that it's easy to see how to do it if you connect it to another problem in quantum algorithms, which is the preparation of Gibbs or thermal states on a quantum computer. Okay, so that's the main message, I think. So this is what I want to tell you. Before telling you that, I want to just to make this connection clear, I want to just briefly mention results on two other problems in quantum algorithms. The first is exactly simulating thermal states, and just briefly mention what we know about it. And the second is this HHL algorithm for linear equations, because then we'll see how what we want to do is a combination of the two methods. Okay, so quantum algorithms, example one. That's just, the canonical one is to simulate quantum physics, right? That's, as I mentioned, Feynman's vision a long time ago, and we learn more and more about it. And I believe one day will be maybe the main application of quantum computers. So if we have a quantum computers, dynamics, we can do very generally, right? For any Hamiltonian, many body Hamiltonian, we can simulate it efficiently. Ground state, sometimes you want to compute, right, the lowest energy, the ground state energy, and the lowest state, a corresponding eigenstate, psi 0. Then not always you can do that, but there are many methods how to do that. You do a diabatic evolution and so on. But there's another class of interesting equilibrium states that we care about, which are thermal states, right? So if you have a Hamiltonian H, the thermal state is just the matrix exponential of that Hamiltonian, where beta is the inverse temperature. You have to normalize to make a density matrix, so that's the partition function does that. And the problem is, given a Hamiltonian, how can you prepare such mixed states on the quantum computer, right? So that's what we want to understand. And we want to prepare it because we want to compute some physical properties, right, like energy or correlation functions and so on. And you see that we want to prepare this to solve SDPs, but you see that later. Okay, so how can we do that, right? So how can we prepare these thermal states? So first, we can always do that. So in the worst case, it's sharply hard to prepare them, even to compute the energy, with high accuracy at least. So there won't be a general method, unlike like simulation, right? Classically, people, of course, care about this problem, and they have good methods, like quantum Monte Carlo. It's quite successful, but that doesn't always work. So in particular, it will fail if there is what we call a sign problem. There was mentioned in the talk before, right? But basically, no, this quantum Monte Carlo, you want to map a quantum system to a classical system in a d-dimensional quantum system in a d+1 classical system. And this mapping is nice for some class of models, maybe like bosons without frustration and so on. But for some models like fermions, doesn't really work, okay? And then you can try to fight that brute force, but it's not really good. So sometimes it gets stuck. How about quantum? Well, if you have the system, the actual system, you could just let it thermalize, right? And we expect that you go to the thermal state. But maybe you want a more controlled method. So there was a bunch of results. Let me mention quickly. We use that later. So Poulan and Vossian, first they showed that using some kind of Grover, we call amplitude amplification, you can always prepare any thermal states in times square root of z times s. D is the dimension, okay? So naively, you can do in times d, right? Which is 2 to the number of qubits. But with Grover, you can get a square root speed up. And that's the sparsity, okay? So there is this quadratic speed up, at least, in the worst case. Then there is like versions of the classical metropolis algorithm. So this is like a Markov chain, but now on eigenstates of the Hamiltonian. And it will converge eventually to the thermal state, but we don't know how long it takes. Okay, so it's like a heuristic. Something you can try, but not always works. But the classical analog is very successful. The quantum we don't know yet, right? It might be as well. At least for high temperature, it works. There's always a threshold temperature. Above the temperature, it works. Then you can see other ideas like quantum heat bath, Glauber dynamics. Then this will be efficient, but you have to assume something about the model, like the correlations have to decay fast enough. So there's a lot of work in this area. We don't know when we can do, when you cannot, but we know some results, right? And these are the results we'll be able to apply later to SDPs. Any question? Okay. Another example of quantum algorithms that is good for us to revise, because in a way what we want to do is a generalization of this, so we have to compare the two in the end, is this work of solving linear equations on the quantum computer. So a linear equation, right, is a very basic problem. We have a matrix A, a vector B, and we know we want to find another vector X such that AX equals B. If you can invert the matrix, we assume we can. That's the solution, right? You just apply the inverse of A to B. So how fast can we do that? That's the question, right? So if A is an n by n matrix, well, even if you want to write down the solution X, it takes times n, other n, right? So you cannot do better than that. But quantumly, we can if we slightly change the rules of the game. So that's the result of these guys. So they show that they show a quantum linear equation solver, meaning that the result is the following. Suppose A is a Hermitian matrix now. Let's assume it's Hermitian. There are tricks if it's not to make it Hermitian. And suppose it's like a nice matrix that we can implement on the quantum computer, this unitary operator, e to the ita for some t. So for example, if A is sparse, you can do that, right? And suppose actually that B is not given in a piece of paper as n numbers, but is given as the amplitudes, as the coefficients of a quantum state, okay? So that's how this is like uniquely quantum, right? And you see that we can do something later for SDPs as well, but let's see this first. Then they show that you can prepare you can solve the system in a way, but in a way that you prepare the solution as a quantum state as well, in time polylogarithmic n 1 over accuracy, sparsity s, and the condition number square. Condition number is the top eigenvalue over the minimum eigenvalue of A. Okay? So for well-conditioned matrices, and if you allow this input in quantum form, and if you're happy with the output in quantum form, that gives big speedups, right? So that's what they do. So the input is in quantum form, as I mentioned. In principle, has many potential applications, like to solve linear differential equations. People propose to use it to solve like electromagnetic scattering cross sections. There are a lot of proposals to machine learning and so on. You always have to be a bit careful because not always this quantum input is is reasonable, right? So that's the drawback here. But yes, Leon. Yes. That's right. Yeah. Right. So yeah, let's talk about sparse, right? Sparse Hamiltonians, right? So then what you assume is that there is an efficient classical algorithm that's given the row, a given row of the matrix, computes you a given row and a given element I, computes the ith non-zero element of that row. If you have such a classical algorithm, right, then you can just turn into quantum and carry superposition, right? So you don't really need Oracle as a black box. You need a classical efficient way of computing, right, all the non-zero elements of a given row, right? Yeah. 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 That's right. Yeah. So that's correct. Yeah. Your problem must be structure, right? That's you have like an efficient way of computing these non-zero elements, right? And that's why most of these applications in machine learning, you have to be skeptical about them, because usually what they think is that you have this classical database there, but there's no structure there, right? And then you have to turn that into a quantum oracle, but that would be inefficient, right? But for some other problems, maybe the matrix is like a Laplacian of a graph, right? And then makes more sense, right? Yeah, but it's a good question. Yeah. Right. Yeah, but it's about like, optimizing numbers then, right? Which people, right? So people have been working on the classic one for decades. Maybe if you put enough effort, you can improve on this, right? But I agree. Yeah, it's definitely a good point that is very important how you have access to this oracle. You need some structures. It's completely structureless, like many times in some database in machine learning, there's no goods. Even if there is structure, like what Dave is saying, there is issues there, but right, it's yeah. So. Right. Right. Okay, great. Right, so why I mentioned this HHL? Well, first, because there's these issues with how you specify the information that will be important for SDPs as well. But also, to mention again, right, so a generalization of linear systems is just linear programming, right? We change equality by inequality. Can we have a quantum speed up there, right? So that's an actual question that we want to address. So just this slide again, that's the SCP we want to solve. Can quantum help? Yes, again, and now we want to see how to do that by connecting to the preparation of Gibbs states on the quantum computer, right? So that's the goal. Why there should be this connection? Well, that comes from statistical mechanics, just Jaynes' principle. So what it says in the quantum case, suppose you have a density matrix rho, a mixed quantum state, and you have some observables, A sub I, and the expectation value of trace of rho on AI equals Ci, okay? Then this Jaynes' principle, or principle of maximum entropy, says that there is a state of this form, a exponential of a linear combination of the Hermitian matrix AI, where lambda I has some coefficients, some real numbers that you have to find what they are, such that these states, right, has the same expectation values as rho on the AIs, okay? So all you care about is the expectation values on AIs. You could just replace rho by this kind of Gibbs states of a Hamiltonian, which is a linear combination of the Hermitian matrix you care about, okay? Well, there's more, so this Gibbs state is the state of maximum entropy with the right expectation values. We won't use that. We will see that that already shows that, next slide I'll show you that this shows that when you want to solve the SCP, we can just restrict to states of this form for the solution. And actually, right, and this makes this connection with Gibbs states. I'll clarify in next slide. But this connection actually, okay, it's very quantum, right? It's a quantum Gibbs state, but this was used before by the classical people to solve SCPs in this multiplicative weight method, right? So they used this connection there. And in quantum information was used before, like to prove, for example, QMA equals P space and some other questions in quantum complexity, but wasn't used before so far to try to solve these problems faster in quantum computing, SCPs faster. Okay, so in more details, right, that's our SCP we want to solve. Just take optimal solution, okay? Sorry, and then the claim is that Jaynes' principle shows that there is an optimal solution of this form, okay? For some lambda j's and lambda 0. So a solution which is the exponential matrix exponential of a linear combination of the input matrices. Why that's the case? Well, take the optimal solution, x optimal, okay? Divide by the trace to make a quantum states. Apply Jaynes' principle. Then we get a Gibbs states with the same expectation values on A, J, and C. But if it has the same expectation values on A, J, and C, it must be optimal solution as well, right? Because this by construction, the Gibbs state by construction is positive semi-definite, right? So it's always, this constraint is always satisfied, and these other constraints only depend on the expectation values. So, right? So that's it. So we can restrict to this kind of solution, okay? And the problem boils down to finding out the lambda j's, right? So if you want to try to implement that on a quantum computer now, what you have to do, well, you have to find a way to prepare, given this Hamiltonian, to prepare the Gibbs state there efficiently, right? To prepare this guy there as a mixed states, and to find a way to find the optimal lambda j's, right? So this is what we will try to do. Yes. Oh yeah, right. Indeed, it's what I mentioned before, right? This is like this maximum entropy principle, right? Yeah. I'm just using it. Indeed. Yeah. It's just the maximum entropy, principle. Yeah. Okay, so let's see what we want to compare to. So I haven't told you about the input model yet. Next slide, sorry, but even classically, if you want to just classically solve this problem, it takes n squared time, right? Because you have to write down the matrix X on a piece of paper, right? Quantumly, at least in the normal model, I'll tell you what it is. Or if you just want to compute the optimal value, not write down the matrix, classical still takes n plus m time. Okay, so you just want to output one number, but it still takes this time. Quantumly, in the normal model, it takes square root of n plus square root of m. So we cannot beat that. Even if all the other parameters, the size of the solution, the sparsity, and the error, they are all constants. They are fixed. And this all follows from just reducing from search problem. So what is the result we got? I'll tell you more details in the next slide, but there is a quantum algorithm for solving SDPs and runs in time T Gibbs, I'll tell you what this is, plus square root of m, and some polynomial, in log nm s r over epsilon. And I'll tell you what this polynomial is. But let me just specify more details what will be the inputs and what will be the outputs. So the input again is a n by n s sparse matrices and numbers as before. I use this normalization. Okay, the operator norm is always smaller than 1. You can always renormalize to do that. And that's important because epsilon is an additive error to the solution, right? So I have to specify scale. This will be the scale. The quantum the outputs, which is what Laura asked before. So I do not require to have x written in a piece of paper that will take n squared time. So I want to do something similar to this linear equation approach. I want to be able just to output quantum samples, so namely a quantum system in the density matrix x over trace x for optimal solution x, and also output the value of trace of x and the value of the optimal plus minus epsilon. Okay? So I want to be able to prepare on the quantum computer optimal solution as a quantum state. And therefore, then we can beat these n square bounds, right? And that's similar to HHL. So what is, again, now this standard, finally this standard model of Oracle. And I'll use another model, which is more like HHL, but this is the first one we'll consider. I'll assume that there is an Oracle that outputs a chosen non-zero entry of any of the matrices at unit cost, okay? So there is a register, there is a, so we have 4 registers. One is like a choice of the matrix. J is the choice of the matrix. K is which row you care about. L is which of the non-zero elements of that row you care about. And Z, and it just outputs XORs with the element there, okay, of that matrix. So it's just the normal model for Hamiltonian simulation, for example, if you know about it, right? And this is the model for which we have this lower bound square root of n plus square root of m, okay? Now you can say, well, actually HHL doesn't, it uses this model for the matrix, but there is this other element, which is the input B, which is in quantum form, right? And we'll see that we can change this later and change the results too. But let's consider this one first, which I think is like probably the most well justified. Okay, so what is Gibbs? So this will have bounds on it, but this is the time it takes to prepare on the quantum computer a Gibbs state of this form. So we just have a Hamiltonian, which is some linear combination of the input matrices, where the coefficients, we have a bound on them. They're at most log n and poly 1 over delta. Actually, this can be like 1 over delta square. And then Gibbs is the maximum time over all these coefficients nu I that takes to prepare such states. Okay. Okay, so how about these other things hidden here? So first, I had a paper with Crystal Svor, and what we got there was Gibbs times square root of m times s squared times r over epsilon to the power of 32. So, right, it's and we claim, speed ups for SDPs on the quantum computer. So, good. But then people in CWI in Amsterdam, Apeldoorn, Gillian, Gribling, and De Wolf, it's the same as ours, but they improve r over epsilon to the 8. It's more respectable, right? Still a bit high. Then with Kalev, Lee, Lin, Svor, and Vu, we actually found out that it's not the product of Gibbs and square root of m, is the sum. Okay, with the same dependence on the rest. And recently, Apeldoorn and Gillian, they improve it, the dependence on the error again. It's r over epsilon to the 4. Okay, so yeah, whatever you do, 2 months later, they do something much better. But yeah, it's, but okay, right? So it's still high, right? Especially because you really care about, like, but for some problems, and I mentioned one, this epsilon is fine to just be some constant, like 0.01, for example, or something. And then this might be helpful. There is this dependence on R, and that's a big drawback. For many problems, as I'll mention later, this R can be big, the size of the solution, and this limits the applicability. But this is something that we're working now to try to improve, and I'll mention some results. But again, the drawbacks of this is in this term. That's why you have to be careful how to apply these results. Okay, so there is this Gibbs that I haven't told you yet how to bound it, right? So, and what we can expect from it. So first, we can use quantum Gibbs sampling, for example, quantum metropolis, and just run this as heuristic, right? And this might give very big speedups in terms of n, if you're lucky enough, and for this Hamiltonian, the system thermalizes quickly, right? So you expect that for many times, it thermalizes in time polynomial the number of qubits, which would be poly log n here. And if that's the case, you're in good shape, right? So you might have big speedups. But of course, we cannot just run and test, so we'd like to know more about this, right? So let's see what we know about bounds in the thermalization time. And now I go back to the initial slides, right? Where I told you. So first, if you just use amplitude amplification, it's a kind of Grover, you can show that this Gibbs is at most square root of n, right? Because n is the size of the matrix, which is like the dimension of the quantum system. So, because we had before, right, this Gibbs plus square root of m, this gives this square root of n plus square root of m. And in terms of n and m, that's optimal in the input model that I'm considering so far. Okay, so because there is this reduction from search. So quantumly, the best classical solver that we know at the moment is like n times m. Quantum really gets like some quartic speed up, right? And we cannot get more than that in terms of n and m, unless we change the rules of the game, which we will later. So let's change the rules of the game, right? So that's optimal, great. Maybe you want a larger speed up. So let's get some inspiration from HHL, from linear equations, and see if we can do something else. And as HHL, actually even worse than HHL, it's very tricky to see how we can apply this in a relevant way. But still, I think it's interesting, and maybe there is more to do. So let me tell you. So suppose the input matrices AI, they are given in quantum form now. And what I mean by that, well, they are Hermitian matrices, right? We can always make them to be positive semi-definite. That's easy. I'll just assume that. So if they are positive semi-definite, we can assume that we have an oracle which gives them as quantum states. So we have an efficient procedure that gives I, prepares the state rho I, which is the normalized version of AI. Okay? So suppose we are given that. And let's B be the maximum over I of trace AI. So this B will be similar like to condition number for HHL. It will play a similar role here. Then we had some results, and then Appledon and Gillian improved on that. They showed that the C Gibbs in this input model is always is of order polylog in n. So now we have this big saves in terms of n and b squared. Okay. So many times this b will be of order n. So then that's bad. But if it turns out that it's not, then you might have bigger speedups here, right? So the total runtime becomes like square root of m polylog n b squared s squared and the same from before. Oh, this should be a 4 here. Right, so it's nice to compare with HHL as I mentioned. So we have this AX equals B. If you assume that these BIs, they are given as a black box in the sense that given I, it outputs BI, then it's easy to show that you need at least square root n runtime, right? Then in that case, you don't have this exponential speedups. But if B is given in quantum form as a quantum state, then you can do something better, right? Here is similar. Again, it has the same drawbacks as this HHL, maybe even more, right? Because, I don't know, I cannot think of many applications where it's natural to think of this AI given in quantum form. But still, we can do something better than these polynomial speedups if you have access to that. So this gives these 3 classes that I mentioned before, right? So as a heuristic, you can try to run this in the normal model, and you might get big speedups in this T Gibbs is small for the particular instance you care about, even though it cannot be small in general. If you have a universal quantum computer, you can always run to get polynomial speedups. And if you allow yourself non-standard Oracle model, you can even get bigger speedups, right? But again, you have to justify if that's a good model or not. Now, what I want to tell you is how I think this kind of solve SCP might be an interesting application for these early quantum computers. Okay, as a heuristic, why I think might be maybe better than some of these other approaches that have been proposed. So quantum SCPs in this noisy intermediate scale quantum era, right? So what is the idea here? So I haven't told you what the algorithm is yet, right? I'll tell you soon. But in the simplest version of it, which has worse scaling, but it will still be interesting for this application. So it runs in times T Gibbs times m over epsilon squared. So there is no savings in terms of m, right? But if T Gibbs is sublinear in n, there will be some savings. The quantum part is extremely simple. So it consists solely of computing expectation values of the matrix AI on some Gibbs states, right? Whose Hamiltonian is a linear combination of the AIs. And maybe this is something that you can run on these small quantum computers, right? So what you have in mind is like a hybrid quantum. So as you see, the algorithm runs as follows. So there's a small number of iterations of order log n over epsilon squared, right? So few iterations. And then in each iteration, the classical computer sends some coefficients nu. At the iteration nu sub t, the classical computer computes these coefficients nu sub it, sends to the quantum computer. These coefficients, they determine a Hamiltonian, sum over I, nu I, ai. The quantum computer should create these Gibbs states and should compute the expectation values with the AIs, right? This is let's call Ci t. Then the CIs are sent to the classical computer. There is a very efficient way to compute the new i's and iterates, okay? So the quantum computer is only being used to solve this. And now the question is, okay, can we do that on a small quantum computer, right? And there's some challenges. The first challenge is that for the for a particular SDP, you get some AIs which has some very unnatural realization as some Hamiltonian, right? And if you have a universal quantum computer, great, but we won't have it. So the first way that I propose to address that is just we want a proof of principle first, okay? So we will not care about the SDP instance that we solve. I just want to solve one particular SDP instance that's the best method, classical method would take a long time. That's all I care about, okay? And then I claim victory if I can do that. I think that would already be interesting. So in the near term, what we want to do is to solve these SDPs, which might not be of practical interest, but that will show a quantum speedup, right? And I think this will be like some halfway between quantum supremacy and really having a practical application of this device. So for example, for my current employer computer, right, that I think I should choose them as an example. So what they can do there, so they have the superconducting qubits, there's like 9 of them, but you have 72 of them in the current plan. And the model there is what we call a Bose-Hubbard model. Okay, so it's like you can treat the quantum mechanical system there as just a bunch of bosons where they have a chemical potential. Like this NJ just count the numbers of photons, of bosons in some sites. Then there's this chemical potential. There's a nonlinearity, right? There's a repulsion if there is more than 2 bosons, a nonlinear repulsion. And there's tunneling, okay, between sites L and K. And they can actually tune these coefficients arbitrarily. So they have a lot of control in the system. So I just want to solve SDP. I just defined SDP as A0 is identity, B0 is 1. This makes X a density matrix. This is good for me. And the other AIs are just Bose-Hubbard Hamiltonians with different coefficients. Okay, okay, Bose-Hubbard is not finite dimensional. We just truncate when the excitation is bigger than 10, for example, because it never very populated anyway in the experiment. Then what? And now the goal is to solve this. Okay, so the classical computer should try to solve this, and the quantum computer as well. So how the quantum computer can solve this? Well, we can use the method. So it has to compute expectation values of the Gibbs states of these Bose-Hubbard Hamiltonians, right? And these AIs are just like local observables, right? That's a nice thing, right? So all of them, we just need to compute some local observables in the Gibbs state of a Bose-Hubbard model, right? Which will be 2-dimensional in that case. For this, right? Because in 1 dimension you could do that classically as well, but in 2 dimensions it's when this can be positive and negative, quantum Monte Carlo, when this is positive, quantum Monte Carlo will fail here. So I'll mention that later. Okay, so we have to compute these expectation values. What I propose to do is we do, again, we could couple to a bath, but we don't have a lot of control, and these computers it will be tough to control the temperature of the bath. But what we can do is coherent evolution. There will be noise, but it's the errors are pretty good. So I propose just to do the coherent evolution according to Hamiltonian until the system equilibrates locally. And that's enough, because you only care about local expectation values here. So the fact that they can use these G's to be positive is great, because then the model has a sign problem, and quantum Monte Carlo will not work. Okay, so that's the biggest drawback for these other problems in quantum annealing. I think because in SDP we can use these fully quantum Hamiltonians, that's a way to make it hard for the classical one. Yes. From product states, yeah. And then you measure, yeah. And then you put that, in. Well, yeah, you only have to measure like this observes locally, right? With local tomography, you'll be okay, but yeah, that's right. Right, so this, I think, well, okay, right, so coupled to a BF is what I mentioned before. Dynamic thermalization is this what I mentioned, right? Is this idea that if, for ergodic quantum system, like when it satisfies quantum chaos, after some thermalization time, which we have to understand, but after that, locally, even though the state overall is pure, because it's coherent dynamics, locally it goes to the thermal state at the same, whose energy is the same as the initial state, right? So the only thing, the point is that for ergodic system, the only thing that is preserved is energy. And all the rest, right, the information is destroyed, and at least locally, and you have this like canonical states. So the idea is just to prepare a product state which has the same energy as the Gibbs state we want to solve, and let it time evolve, and then in that way, mimic thermalization, but with a unitary process, right? Which I think will be very helpful for these small quantum computers. Now the question is whether this Bose-Hubbard model is ergodic or not, right? And in 2 dimensions we don't know, especially because it's hard to simulate it. But in 1 dimension there is a paper where people, computed things and they saw this after very short time, after just a few like clock times of the evolution. So there is hope that it might work in 2 dimensions. If it actually works, we don't know, right? So we have to run and see. But that's what I propose. So what I'm doing here is just to propose this SDP as a kind of a generalization of annealing, right? Which is a problem that people have been studying more. So how we see that is a generalization. Suppose you just want to compute the maximum eigenvalue of a matrix C. That's a very easy SDP, right? So you can write like that. Maximum trace X. Trace X is 1, X is positive semi-definite, right? The solution, C is Hermitian, so it's the maximum eigenvalue. So people try to solve this problem, especially when C is classical, right? It's just like a cost function of some hard optimization problem by quantum annealing, right? Where you cool down or you do a diabatic evolution. So that's the example of maxcut. I'll just jump that. So basically what we're doing here is a generalization of that, right? So let's compare quantum annealing with this quantum SCP. So in quantum annealing, the final Hamiltonian is classical, right? Again, it's this cost function of some optimization problem you want to solve. In SDPs, it's a fully quantum Hamiltonian, right? It's this Hamiltonian, which is this linear combination of the input matrices of the problem. But for SDPs, it makes a lot of sense, right? And usually it's the case that these are not diagonal, right? So they are fully quantum. So the temperature for annealing ideally is 0. So if you want to solve the SDP with error delta, it's easy to show that the temperature has to be delta square. Okay, so that's maybe a little bit better. We have this control, which is hard to get here in general. Preparation, you can do many ways, right? You can do cooling, you can do a diabatic evolution, this QAOA. For STPs, you can do cooling as well, and you can do this dynamic equilibration, right? But maybe there are other methods that I would like to know. How about the runtime? Again, both are like heuristics, right? At least in this way. So here, what matters is the minimum gap, for example, for the diabatic evolution in quantum annealing. For quantum SDP, what matters is the C Gibbs, right? So these 2 things, these physical quantities that we just have to, it's hard to get a control of them, right? I gave you some bounds with a universal quantum computer. With small quantum computers, we have to run and see, right? But maybe you're lucky. So I think that might be a nice thing to test because these SDPs, they're exploring more fully the quantum features, right, of the device. And they can more easily beat quantum Monte Carlo, which was a big challenge here, right? It's still a big challenge here. Okay, so I wanted to tell you some application, but I'll jump that. So I'll just mention that this R dependence is a big problem in general. Many problems, well, it was before here. Many problems, they have big R over epsilon. So actually, you can always trade R by epsilon. So you should think R over epsilon as one fixed quantity. You can change one by the other. But many combinatorial optimization problems, which is a big application of SDPs, they have very big R over epsilon. And therefore, there is no direct speedup. Okay, so this limits the applicability considerably of the methods. So the question is, can we do something better? And I just want to, I'll jump the details, but I just want to mention the result that we recently got with Daniel Franz and Richard Quinn, who is here, which is for this canonical Goldman-Williamson SDP, which is the first SDP proposed for optimization problems for max cuts. There is a minor speedup. Okay, you go from for a graph with n vertices and degree d, you go from order n times z, which is optimal classical, to quantum n square over square root of d. So sometimes the quantum is worse, but if the degree is big enough, right, bigger than n over 3/2, I guess, then there is a minor. Okay, so there is some progress on this barrier of R being big. I won't tell you the details. I don't have time. But it shows there is still a lot to do, right? So the fact that we have this speed-ups in terms of n and m is not the end of the story, because you have to understand the relevance of R, and that's a hard problem. Well, it's a harder problem at least, but we're trying to make some progress, but I think there is a lot to study here. So let me jump that, because I want to tell you about the algorithm, right? So in the last 5 minutes maybe. So what do we want to solve? So we want to find, let's map to this feasibility problem, which we can always do, I promise you. So we want to find a density matrix such that we want to see whether there exists a density matrix such that the expectation value of rho on AI is smaller than BI. By Jaynes' principle, as we saw before, we just have to find these lambda i's. And I propose to do as follows. So we'll start from a guess, which is I have no idea what rho is. So rho is just the maximally mix initially. And then we will iterate rho. We will like make better and better guesses. So the claim is that if you run from t from 1 to 16 over log n over epsilon square, the following, you solve the problem. So first, we do quantum Gibbs sample, right? So by some procedure, we prepare the Gibbs states of square root m copies of rho sub t. Okay? And initially, rho 0 is just maximally mixed. Then we do Grover search over I to find a I which violates the constraint, right? So for a feasible solution, trace AI rho t should be smaller than bi, we search for I, which violates it by some factor epsilon over 2. And we let it be I sub t. If you cannot find this, then we solve the problem already, right? We find an approximate feasible solution. We are happy with that. If we can't find this violating, then it means that our solution, our guess for the solution rho sub t is not the right one yet. And then we penalize in the direction of AI by adding it to the Hamiltonian. Okay, so we see rho t as a Gibbs state. This log of rho t gives the Hamiltonian, and we just add a penalty of minus epsilon square AIT to that direction. So it's some kind of gradient descent, but you do that to the Hamiltonian, to the exponent of the matrix, right? Okay, so first, what is the runtime? Well, by phase estimation and amplitude amplification, Gibbs sampling takes at most square root of n, right? So the number of iterations is very few, is log n. And each iteration you have to prepare square root of m copies, and each copy takes time square root of n. So it gives total square root of m times n time, which is this first thing that I mentioned, right? There's tricks to map to the sum. I won't tell you. This follows from, it's called like quantum OR bounds, or a faster way of this quantum OR bound. This gives the sum, but never mind. But that's the basic idea, right? It's kind of simple. Why, maybe, should I skip? I'll go very quickly, but because I don't have time. But why this procedure works, right? Why this simple procedure actually gives a feasible solution. So that's because of this actually nice inequality using relative entropy. So by some matrix inequality, it's called Peirce-Bogoliubov. You can check on Wikipedia if you don't know it. You can prove this. You can prove that there is a cost function, which is the relative entropy of the feasible solution rho to the guess, rho sub t, for which it satisfies this. So the difference of the cost function at time t and time t minus 1 is smaller than minus epsilon over 8 trace a I sub t rho minus rho t. So whenever, right, there is a violating constraint, this has to drop, right? So if Grover's search never fails, it means that for each t, this guy here, well, this is wrong. It should be epsilon square over 8. It means, I know it's correct. It's correct. If Grover's search never fails, right, it means that this is true, right? So the cost function has to drop by epsilon square over 16. But initially, the relative entropy, rho 0 is a maximally mixed state. So the relative entropy is log n. And each time it can drop by at least epsilon square over 16. So after 16 log n over epsilon square, if it always drops, the relative entropy would be negative. But that's impossible, right? So it has to stop before. So that's the proof. It's pretty easy. It's basically a gradient descent on the exponent, and you have a nice cost function. And we're using the exponent because the cost function then, the maximum value is log n, and that's very good for us, right? So that's all I want to say. So conclusion, we know many quantum algorithms, right? And that's why we want to build a quantum computer. We would like to have more, of course. Many times it's challenging to find more. And first, some excuses, right? So first, we don't have a computer yet, so it's hard to get intuition, as we have with classical computing. Secondly, we must compete with decades, right, of advances in classical algorithms. That makes it hard. I think that these quantum SDP solvers, or more general convex optimization problems, they are interesting area to explore because they involve an interesting combination of I guess, different quantum algorithm frontiers. So there is some aspects of HHL, linear equations, some aspects of Gibbs sampling, like quantum metropolis, and some connections with quantum annealing, right? Each one of them, it's a fruitful area, so combining them is a good idea. There are many open questions. So first, can we find relevant settings with larger speedups, right? Either using this heuristic or using this input model 2. I don't know. That will be interesting. What is the complexity of solving Goldman-Williamson? We have this tiny speedup. Maybe it's bigger. On the other hand, we don't even know any lower bound. It could be that we have exponential speedups. I doubt it, but I don't have a proof yet that we cannot have it. How about SDPs for general combinatorial optimization problems? Can we always get a speedup there? It's not clear because of these R parameters, but this speedup for Goldman-Williamson gives hope, right, that it's possible. Can we improve the dependence on R or error, right? And remember, interior point had log R of epsilon. That was great. Can we do something quantum interior point? We don't know how to do it. At least I don't know. So what is the robustness to error, right? To understand it more deeply would be interesting. In particular, can this quantum computer be a good proof of principle for these NISQ devices? That's also a problem that I want to understand better. So with that, I stop here.